Okay, I'm going to show you how to make an interval vector and an index vector. We're going to start with the interval vector. The interval vector is just a table of all of the intervals that exist in a given collection of nodes. And the intervals are interval classes. So that means we have 6 possible interval classes that will form our table here. So here they are, interval classes 1, 2, 3, 4, 5, and 6. Now remember, an interval class is the smallest expression of an interval, the smallest space within which you can fit 2 nodes. Okay, so we will start by comparing all of the nodes to D, the first node in our collection here. So D to E is a whole step. So that's a 2, that's interval class 2. D to F is a minor third, or interval class 3. D to A flat is a tritone, diminished fifth, or interval class 6. And finally, D to A, that's interval class 5. Now you might think, well, isn't that 7 half steps? Well, it is if we put the D below the A, but if we put the D above the A, then it's a perfect fourth, and it's 5 half steps. So remember, the interval classes are the smallest expression of 2 nodes, the distance between 2 nodes. So we've done all of the intervals with D, so now we move on to E. So E to F is a half step. That's a 1. E to A flat is 4 half steps. Think of that as a G sharp. That would be a major third, which is 4 half steps. And E to A is a perfect fourth, or 5 half steps. Put a jog there. So now we've completed the intervals going up from E. So now we move over to F. F to A flat, that's a 3. F to A, that's a 4. And now we move over to A flat and do our last interval, which is A flat to A. That's a 1. So we have now the table. It's completed. It's 2, 1, 2, 2, 2, 1. So this is our interval vector. This means that if we were to, say, transpose our collection by a half step, that would be interval class 1. That could be a half step up or down. We're going to get 2 common tones. So if we transpose it by 2, we're going to get 1 common tone, and so on. The only interval here that's an anomaly is the 6. It looks as though we would only have 1 common tone if we were to transpose by 6 half steps. That's what the table tells us. But actually we would have 2 common tones in this case only. It works like this. Tritone maps into itself, so the D would transpose to A flat if we were to transpose by 6 half steps, and the A flat would transpose to D. So even though there's only 1 tritone in the collection, it results in 2 common tones. So we always have to multiply whatever we get for a result under the interval class 6. We have to multiply that by 2 times 2. So we get 2 common tones. So that's really the only thing you have to remember here. Is that one little aberration. Okay, let's just try one, so you see how it works. So let's do the, I think I'll transpose by half step. That's interval class 1. And this tells us we should have 2 common tones. So let's see if we find them. So there's D would transpose up to D sharp. The E would transpose to F. Right? So there's 1 common tone. The F would go to F sharp. The A flat would go to A. There's our 2nd common tone. And the A would transpose up to B flat. So the collection would be D sharp or E flat, F, F sharp, A, B flat. And the 2 common tones are F and A. Now let's transpose down by a half step. So D would transpose down to C sharp, E would transpose down to D sharp, F would transpose down to E. There's our common tone. One of them. A flat would transpose down to G. And lastly, A would transpose down to A flat. There's our second common tone, A flat. So in this case, the E in the A flat would remain common to those two transpositions. Okay. So I think you get the idea, and that is the interval vector. And I'll be back in a moment, and we will make an index vector. Okay, I'm back, and we're going to use the same little 5-note set to make our index vector. Okay, a little review first. Remember in class we looked at the clock face, and I drew a clock face to just to kind of show how inversion works. Okay, so here's the clock face, and just populate it with the numbers that we need. Okay, so I'm just going to choose, let's see, I think I'll just pick 3 notes, and then we'll examine how they behave under inversion. So I'll just randomly choose a C sharp, that would be a 1, a D, which would be a 2, and an A flat, which would be 8. Okay, remember that we map 0 onto C, C sharp, 1 and C sharp are mapped together. D is 2, E flat is 3. It's just a chromatic scale with C being 0. So 1 is C sharp, 2 is D, 8 is G sharp or A flat. I'll just call it an A flat. Right, so if we were to fold the clock face right down the middle here, what would happen is that the numbers that I've selected, or the notes that I've selected, would jump to the other side of the clock. So the 1 would move over to the 11. It would touch the 11 if you folded it in half, right down the middle. And the 2 is going to go all the way over and become 10. The 8 will go this way, and it's going to become 4. So 1, 2, 8 is going to turn into 11, 10, 4 if we were to fold the clock face down the middle. Now we'll notice that if we add these notes together, add these numbers together, I should say, so 1 and 11 is 12, 10 and 2 is 12, and 8 and 4 is 12. So the number it becomes, 1 becomes 11, 2 becomes 10. Those are all adding up to the same number, which is 12. But we call 12 0 in this system. It's what's called a mod 12 system. So we don't go beyond 11 with the numbering. Once we go beyond 11, it goes back to 0, which gives us our 12, our set of 12 numbers or 12 notes. So anything that goes beyond, anything that's 12 or higher, you need to subtract 12 from that to keep it in this circle. Now, in other words, let's say we came up with a 13 when we're adding things together, which you're going to see later on. Then we would subtract 12 from the 13, and we would get a 1. It's like we go from 0 to 1, or 12 to 13, but we don't call it 12 to 13. It's good. 0 to 1. So just remember that. That's what's called mod 12. Okay. Let me remove some of these markings now, and what we'll do now is let's do a different folding of the clock face. So instead of folding right down the middle, which gave us index 0, in other words, everything was summing to 0, we're now going to fold the clock face between the 0 and the 1. And so now this C sharp would become a C, the 1 would become a 0, and the D would become a B, the 2 would move to 11, right? So 1 would move to 0, 2 would move to 11, and the 8 would move to 5. So what are these numbers summing to? Well, they're summing to 1 or 13, right? The 1 becomes 0, the C sharp becomes C. That's a 1 and 0 equals 1. 11 and 2 add up to 13. Minus 12 is 1. The 8 and the 5 add up to 13. Minus 12 is 1. So if we fold the clock face in this fashion, we are going to have sums of numbers that all sum to 1. That is, numbers that are exactly directly opposite on the folding of that clock face will all sum to 13 or 1. So that's index 1. Now we can fold the clock face right on the 1, and that would also be on the 7. That's going to make everything sum to 2, so this would be called index 2. So the 1 would stay where it is, but 1 plus 1 is 2. The D, which is on 2, is going to become a C. It's going to end up over here. And that sums to 2. And the 8 is going to move over to here to the 6. That's directly opposite on the clock face if we're folding it along 1 and 7. And that's 14 minus 12 is 2. So all of these are going to sum to 2, so therefore that's called index 2. The next index would be here between 1 and 2 and 8 and 7, so that's index 3, which is also 15, right? 8 and 7 is 15. Minus 12 is 3. So that's index 3. Okay? And then if we fold it along the 2 axis, that's going to be index 4. 8 plus 8 is 16, minus 12 is 4. If we fold between the 2 and the 3, that's going to be index 5. Along the 3 is index 6. Index 7 is between the 3 and the 4. Index 8 is right along the 4. Index 9 is between 4 and 5. Index 10 is right on the 5. And index 11 finally is between the 6 and the 5. And all of those numbers, if we collapse the clock along that axis, would sum to 11. Okay, so there are only 12 index numbers. Like once we've done this, we're going to be right back to this again, which is where we started, index 0. So that's how that works. Erase this all now, and now we'll make our table. So I just wanted to review that though, so that at least you see how these index numbers are derived. Right, okay, so first thing we need to do is turn our little pitch set here into numbers. So D is 2, E is 4, F is 5, A flat is 8, and A is 9. Again, these are just the numbers that would represent these notes if we were to make a chromatic scale starting from C and just going up. You know, C is 0, C sharp is 1, D is 2, and so on. So these numbers represent these notes in that system. Now, to make an index vector, really what we're dealing with is the adding of numbers, because that's how these indexes, how those index patterns that I just showed you with the folding clock face, that's how they work. So we make a table by first making kind of like a little graph here. And along the horizontal axis, along the top here, which we call the horizontal or the x-axis, we simply put in these numbers. So 2, 4, 5, 8, and 9. And now along the vertical axis, or sometimes called the y-axis, put in the exact same numbers again. 2, 4, 5, 8, and 9. And now what we're going to do is simply add all the pairs of numbers together. So we take the 2 and add it with the 2, and that becomes a 4. Let me, I'm going to have too many markings on the graph if I don't erase them as I go. So we got a 4 there. Now we're going to add the 2 with the 4, and we're going to get a 6. And we're going to add the 2 next with the 5, and we get 7. And then we add 2 with 8, and we get 10. And 2 with 9, and we get 11. Okay. Now we move to the 4, the next number here in the vertical column, and add that to the 2. We get 6. All right. And then we add 4 with the 4, and we get 8. And then 4 with 5, it's 9. 4 with 8 is 12. 12 is 0 in our system. Remember, if it's 12 or higher, we have to subtract 12 from it. And then 9 and 4 is 13, but that's 1 in our mod 12 system. You subtract 12 from the 13 and we get 1. Now we move to 5. Add 5 with 2, it's 7. Add 5 with 4, it's 9. 5 and 5, 10. 5 and 8 is 13, which is 1 mod 12. And then 5 and 9 is 14, and that's 2 mod 12. We subtract 12 from the 14. We move on next to the 8. 8 and 2 is 10. 8 and 4 is 12, which we know is 0. 8 and 5 is 13, which we know is 1. 8 and 8 is 16, so minus 12 is 4. 8 and 9 is 17, minus 12 is 5. And now the last group of numbers here, 9 and 2 is 11. 9 and 4 is 13, which is 1. And 9 and 5 is 14, which is 2. 9 and 8 is 17, minus 12 is 5. And 9 and 9 is 18, minus 12 is 6. So now we've finished all of these additions. So the next step is to make the table. So remember, there are 12 index numbers, 0 through 11. So I'm just going to make a list here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Those are our 11 index numbers. And now we have to figure out how many of each of these numbers showed up in all of this addition that we just did. So how many zeros are there? I find 1, 2. So I put a 2 under the 0 column. That means there will be 2 common tones if we apply index 0 to our collection. How many 1s are there? So 1, 2, 3, 4. So I put a 4 under index 1. 2, there are 1. Looks like 2 2s. And there are no 3s, so I put a 0 there. There are 1, 2, looks like just 2 4s, yeah. Okay, so we put a 2 there. And how many 5s? 5 here, 5 here. Looks like 2 5s. There are 3 6s, it looks like. 1, 2, 3. There are 2 7s right there. Looks like only 1 8. 2 9s. 3 10s. And lastly, 2 11s. Looks like we got them all. Okay. I always like to double check when I do this by making sure I have the right number of solutions here. So, right number of additions. So there are 25 numbers that we found. 5 across, 5 down. So this group here, we have 25 different numbers. So these numbers here should add to 25. So 4 plus 2 is 6, plus 2 is 8, plus 2 is 10, 12, 15, 17, 18, 23, 25. So more than likely we did this right. Okay, so that's basically it. That's how you make the index vector. It's all contained right here. And now let's just do one. Let's just test one out. And actually, before we do that, it's interesting to examine the numbers we found. Like, for example, index 3 yields no common tones. So that's an interesting bit of information. Maybe if we're using this collection and we want a high degree of chromaticism, we want to make an inversion, we might go for index 3 because we're going to get a whole new set of notes. If you don't want things to move that quickly, you could go to index 1, which is going to give you 4 common tones. So there's going to be very, very little movement. There's just going to be one new note that'll show up if you apply index 1 to your collection. Let's try index 3. So what we do is we just take the 2, 4, 5, 8, and 9, and we find the numbers that we need to produce the result 3. Like 2 plus what equals 3? Well, 2 plus 1 equals 3. 4 plus negative 1 equals 3. But remember, 3 is also 15 in mod 12. So we can ask ourselves, 4 plus what is 15? 4 plus 11 is 15. 10 plus 5 is 15. 8 plus 7 is 15. 9 plus 6 is 15. So here we can use those larger numbers to just go through this quickly. So 15, remember, is 3 mod 12. All right, so this would result in the notes C sharp, B, B flat, G, F sharp. And remember, our original notes were D, E, F, A flat, and A. No common tones between those two groups. And this, of course, the lower collection, is the inversion of that. D goes up to E, C sharp goes down to B, E goes up to F, B goes down to B flat, F goes up a minor third to A flat, B flat goes down a minor third to G, A flat goes up a half step to A, G goes down a half step to F sharp. So there we have an inversion. We applied index 0, index 3, so that we would get 0 common tones. And that's the result. Okay, that's it. Thank you.